Hi, my name is María José Loor. The topic to be discussed is Streamlining Flexible System Design using RF ADCs with DSP. Next, I will deal with 4 important points. Number 1. Definition. The highly integrated and versatile RF ADCs support a wide variety of system design with their DSP feature set. For DC device alleviate the complexities of system design from today's radio architectures. Next, a video.
Hello everyone, I'm Marjorie Plish from Texas Instruments here in Silicon Valley. Radio designers are always looking to increase system capacity while reducing the size, weight, and the cost of their boards. TI's complete portfolio of 8-bit, 10-bit, 12-bit, and RF sampling gigasample ADCs provides an elegant integrated solution to this problem. With that, TI has revolutionized radio architectures by enabling a new generation of high dynamic range, wide bandwidth, software-defined radio applications. An RF sampling ADC means no analog frequency down conversion is required, as in a traditional IF sampling or zero IF sampling design. These ADCs can eliminate many analog components including mixers, LO synthesizers, amplifiers, and filters. This reduction in component count also simplifies and speeds up the design process. The benefits of an RF sampling ADC apply across a wide variety of applications, including 3G and 4G base station receive and digital predistortion, wireless backhaul, military communications and signal intelligence, data acquisition, radar and LiDAR, optical networks, software-defined radios, and even multi-tuner set-top boxes. The recently released RF sampling gigasample ADCs build on the huge Nyquist zone and excellent dynamic performance of TI's existing gigasample per second devices, with improved performance and additional capabilities. Some of the beneficial features include excellent dynamic performance up to 2.7 GHz inputs and beyond, sample rates up to 3.6 gigasample per second, the industry's largest high-resolution Nyquist zone at 1.8 GHz, and pin compatibility with TI's 10 and 12-bit ADC families, allowing designers to easily explore a wide range of speed and resolution combinations. Let me show you how these ADCs enable RF sampling in a base station application and how they enable performance in architectures which are not possible with existing ADCs. What we have here is the ADC 12D1800 RF evaluation platform. It includes an FPGA and the WaveVision 5 software tool for measuring the ADC performance. The RF sampling evaluation board also includes an FMC connector to allow the option of streaming data at full data rate to a compatible data acquisition board. For 3G, 4G base stations, the RF frequencies typically range from about 700 MHz all the way up to 2.7 GHz. This screen shows the performance of the RF sampling ADC with two tones around 700 MHz. In this case, the IMD3 is negative 67 dBc, which is similar to traditional base station ADCs. Now that we've considered the lower end of the base station RF spectrum, it's more interesting to consider the high end at 2.7 GHz. So let's look at the performance with two input tones around that frequency. At 2.7 GHz, traditional base station ADCs don't even operate. However, this RF sampling ADC maintains excellent performance out to 2.7 GHz, yielding negative 64 dBc at 3600 megasamples per second. So you can see that with these RF sampling ADCs, you can directly sample RF inputs for base stations and many other applications, eliminating one or more frequency down conversion stages entirely. Whether you're looking for a better integrated solution for 3G and 4G base stations, reduced size, weight, and area for military designs, much higher data capacity for microwave backhaul links, or the ability to do on-the-fly digital control of frequencies and bandwidths for software-defined radios, the recently released Direct RF Sampling ADC family and the entire 8, 10, and 12-bit gigasample ADC portfolio from TI provides an integrated solution that meets all of these challenges while reducing cost and design time. To get design resources and more information on these and TI's entire gigasample portfolio, please visit us at ti.com/gigadc. That's going to wrap things up for today's video. Thank you for watching, and we'll see you again next time.
Point number 2. Applications. The ability to capture a still or moving image, radio transmission, and radar sonar signals, and to turn them into actionable information is growing rapidly in importance for military organizations around the world. The requirement is not only to capture increasing numbers and types of these and NILO phenomena, but to transmit them more quickly, to process them more especially, and to deliver intelligence more swiftly than ever before. Military, electronic warfare, electronic countermeasures. ISR, intelligence, surveillance, and reconnaissance, and human vehicle telemetry system. Others, single intelligence, multifunctional radar, and radar sonar. Number 3. Pros and cons. Pros. They can be deployed in human vehicles. Systems must be prepared to meet the modern threat of electronic warfare. They have long end-to-end latency, high watt-width. They have latency inherent in the interconnection of ADC and DAC to FPGA. Cons. Software-defined radio SDR uses software to replace the hardware components of a radio communication. In SDR, it is possible to modify their characteristics during radio operation. SDR architectures can also be dynamically reconfigured and adapted to multiple hair interfaces, enabling active antennas and beamforming for defense electronics. Next, a video.
From Keysight Technologies, and I'm presenting on behalf of my colleague Dr. Murthy Upmaka. Murthy is an application engineer in our Eastern U.S. organization and works with many radar customers. And he has a methodology paper that talks about the benefits of model-based design as well as co-design of RF and DSP together. In most organizations, and this is nowhere any less true than in defense organizations, the baseband FPGA signal processing community is often very separated from the RF community. Sometimes this is a matter of meters across an aisle, sometimes it's across a building, sometimes it's across entire cultures and tool sets. And what happens in an organization that is kind of separated, where you have individual design flows is that they don't talk to each other and co-validate along the way. And there's some costs associated with an inability to do that. In an organization that is able to speak, the algorithm guys, radar signal processing, for example, or in 5G, the communication signal processing, have a hard time taking into account RF impairments in the signal processing to know what it is that you can really get away with or what needs to be corrected. The RF guys generally have static models of the signals moving through CW or multi-tone, and they aren't able necessarily to see how their systems are being used, their infrastructure. And the system architects have a hard time bolting these things together because they have an imperfect way to predict the performance, and what you end up doing is over-designing both sides of this. So if you're able to do co-validation along the way and build bridges between design and verification of partitioning and reintegration, and actually do that integration step along the way and co-validate, you can design out design margin, and not over-design some of your platforms quite as much. And you can accurately account for some of these things and find the cheapest place to solve a problem. Sometimes it's cheaper to solve it in a better signal processing algorithm. Sometimes it's better to just buy a better amplifier. And to be able to know where's the best place to solve a problem and be able to validate it is part of the benefits of an integrated approach. So with that, Dr. Maka, who wrote this, wanted to pose a few challenges. One of the challenges is that RF circuits and subsystems are usually done in the frequency domain, and even when they're simulated in the time domain, the concepts are really frequency domain anyway. And so the signal processing guys are all in the time domain, very dynamic behaviors, and they aren't able to render some of the RF. And what happens is, in the RF, you either have a very detailed RF model that you believe intimately, but you have to simplify the signals, or you go on the baseband side and you have arbitrary signals, but you have very simplified RF. And so
Number 4. Issue applied in Ecuador. Mobile device manufacturers and packing more method of wireless connection into their design. Bluetooth, WLAN, WiMAX, and GPS, in addition to 3H and LTE broadband, to satisfy the demands of the marketplace. Multifunctional radar with multi-core processors. RF ADC feature set AD 9208, AD 9689 block diagram. As the picture shows. The conclusion, or in conclusion, DC devices are used to capture or transmit analog signals from acoustics to radio frequency, high process definition video for storage or transmission over a long wide network. stream high watt-width data over long distance via optical links, or even process existing digital data through high capacity and energy efficient FPGA device. Thank you.